All right, everybody, good day. I hope you're doing well. I wanted to go through a few other applications with you regarding differentiation. Last week we looked at curve sketching, and I posted a whole bunch of additional examples for you to look at. Today we're going to be going through related rates. You may have talked about this a little bit in high school, I'm not sure, but the general idea is that when you're looking at mathematical models for something, in real life, usually time is defined implicitly. And in order to examine how things change with respect to time, you would have to do implicit differentiation for such models. So we're going to do a couple of examples, but the general approach is always the same. The first thing that we do is identify all the quantities that we have and the ones that we need to figure out. And if possible, I highly recommend that you draw a sketch of the situation. It really does help in order to help you visualize what's going on and what parameters correspond to what. The next thing is we write an equation relating all the variables of the problem. So the first example we're going to do, for instance, has to do with an icicle that's sort of dripping, and it's getting longer, but it's also getting skinnier, not quite as wide. And so an icicle would be in the shape of a cone, so you would use the equation of a cone. If you're talking about, bacteria that's growing in a circle and spreading outwards, you would use the area of a circle. So usually it's somehow related to either volumes or areas. And then the next thing is you implicitly differentiate to find the derivative on both the left-hand side and the right-hand side of the expression that you're using, and with respect to time. And then we solve for whatever the derivative is that we're looking for. And we're typically given quantities. The radius of the icicle is decreasing at a rate of, 0.02 centimeters per hour, or something like that. So you'll be given those types of numbers. And that's the general idea. Once you have your derivative, then you sub in what you know, and then you just isolate for whatever derivative you want. So let's start off with example of, icicles. We have an icicle. So a cone-shaped icicle is dripping from a roof. The radius of that icicle is decreasing at a rate of 0.2 centimeters per hour, while the length, as it's dripping, is going to be increasing at a rate of 0.8 centimeters per hour. If the icicle is currently 4 centimeters in radius and 20 centimeters long, is the volume of the icicle increasing or decreasing, and what is the rate of that? So in our situation, the image that we would draw is a cone that represents an icicle, where we haven't been given variables, but the thing that's important here is the radius of this icicle and the height of this icicle. Okay, so we're going to say, well, we're going to let R be the radius, and we're going to let H be the height. Okay, and in my diagram here, what I'm going to do is draw this as the height. Okay, so this is my H, and then my radius of my icicle, okay, corresponds to that value there. And we know the formula for the volume of an icicle. Now, why am I using volume? Because we want to know if the volume is increasing or decreasing. Okay, so for this problem, we need the formula. Oops, sorry, my head's in the way. For the volume of a cone. Okay, and we know what that is. If you forget, that's not a problem. You can look it up on Google, but it's 1/3 pi r squared times h. Now, remember, when we're writing this down, this cone, its volume is changing with time. its radius is changing with time and its height is changing with time. So really we're thinking about this as being a function of t. 1/3 pi is a constant, but r is really a function of t because it changes with time. And so is the height. And so what we're going to do is we're going to differentiate this. Okay, t is implicitly defined, so we'll use implicit differentiation, which just means we have to make sure that we're using the chain rule. Okay, so differentiating with respect to time gives, so on the left-hand side, we'll have a dv dt, and then we're going to have 1/3 pi. These are constants, but I have to be careful here because my r and my h are both functions of time. So we're going to have to do the product rule for this. So I'm going to put big brackets here, take out my constants to make sure I don't forget them, and I'm going to go the derivative of the first, okay, so the radius squared. So by product rule, I'm going to bring down the 2, I'm left with an r, but by chain rule, I have dr dt. And then, so the derivative of the first times the second, just h, plus the derivative of the second. Okay, so the derivative of h is just 1, but then we have times dh dt by chain rule, times the first. So that is r squared right there. Now, what are we looking for? We're looking for dv dt. So in this case, I don't have to rearrange for any of the derivatives here. But a question is, do I know what these derivatives are? And I do. In my problem, I'm being told that the radius is decreasing at a rate of 0.2 centimeters per hour, and the length is increasing at a rate of 0.8 centimeters per hour. So the increasing at a rate, decreasing at a rate, this means derivative. And when we're decreasing, it also means that in front of this 0.2, we actually have a negative sign. Okay, so we have, or we're told, we are told that our dr dt is equal to negative 0.2, and this is centimeters per hour, and our dh dt is equal to, it's increasing, so positive 0.8 centimeters per hour. Okay, so that means that we have this quantity here and we have this quantity, but what about our r and what about our h? Well, we're also told in the problem, if the icicle is currently 4 centimeters in radius, so our r for the time that we're interested in is going to be 4, and the length for the time we're interested in is going to be 20 centimeters. Okay, so I also know for the time we are interested in, r is equal to 4 centimeters, and h is equal to 20 centimeters. So that means our expression here, our dv dt, this is going to be equal to 1/3, and I'm going to put the pi actually up top here. And then I have 2 times, my r is going to be 4, my dr dt, that's the negative 0.2, and my h is going to be 20. My dh dt is going to be 0.8, and again my r is 4, and in the second term it's actually squared. Okay, so if we simplify that, I'm going to get this is equal to, it turns out to be negative. Okay, this term is much larger than this term. So I'm going to have pi over 3 times negative 19.2. Okay, so if you multiply this out, we're going to get that, you know, actually you can even leave it like this if you want to. We can say negative 19.2 times pi over 3. Now, what is my units here? Well, volume is something cubed, and we're doing everything in centimeters. So this would be centimeters cubed. And on the bottom of this derivative, we're talking about the rate of change of time. So this would be centimeters cubed per hour, because hour is the quantity for time we're talking about. And because this number is negative, it means that the volume is decreasing. So the volume is decreasing at a rate of dV dt is equal to negative 19.2 pi over 3 centimeters cubed per hour. Make sure that at least in your final answer, the final statement, you do state what the units are, okay, the dimensions of this, because there will be marks assigned for that. Okay, so there's one that it's probably easier for you to visualize because we've all, or most of us, have seen icicles, at least if we grew up in Canada. Okay, now let's do one where we talk about blood flow. Now, when you have blood flow through a vessel, did I say vessel? Is it supposed to say vessel? A vein, basically. So like a circular vein, think about just like a straw or a cylinder. It turns out that the flow of your blood is faster in the center because of something called boundary conditions. If you look at like a little stream, next time you're out walking, look at a little stream either from the rain going down the sidewalk or an actual stream itself. If you look at the very edges, you'll notice that the water is not actually moving. It's a specific type of boundary condition that you learn in fluid mechanics or fluid dynamics. So in the center, it moves the fastest. Okay, so this is according to a particular fluids law. And for our problem here, they're saying that the velocity, and they're calling it V of blood, is given by this. Okay, K is just a constant, specifically constant, and we're assuming for us it's going to be equal to 375. But the general rule in fluid dynamics is this, that the velocity is equal to some constant times capital R squared, where that capital R is the radius of the blood vessel, okay, or the vein or whatever. And then the little r is the distance of a layer of blood flow from the center. So and then we'll read this in a second. So suppose that, you have blood flowing through here. It's going to be fastest along the center. And as you move out, when you finally hit the wall, the velocity is going to be equal to 0. Okay, so we're going to suppose that a runner's blood vessel has a radius of 0.08 millimeters, and that, maybe they're running outside in the cold, which I like doing in the winter. The cold weather is causing the vessel to contract at a rate of capital dr dt of 0.01 millimeters per minute. How fast is the velocity of the blood changing? Okay, so if it's contracting, right, if the blood vessel is contracting and getting smaller, that's going to influence the actual speed of the blood flow. Okay, because that means that there's not as much room in the center where the blood can go the fastest. So if we make it smaller, overall everything's going to decrease in velocity. So what is it that we're actually looking for in terms of a derivative? So how fast is the velocity of the blood changing? So the rate of change of velocity. So we're looking for dV dt. So we want dV dt for this problem. Okay, and in our situation, we're told that the constant would be 375. Okay, so we have, and remember the velocity of the blood, so that's changing with time. So really this is a function of time, is equal to 375, a constant. And we're being told that the vessel to contract at a rate of dr dt. So the capital R is changing with respect to time, but the little r, flip back here for a second, this little r, the distance of a layer of blood from the center, that's going to stay the same. So we think about that little r like a constant. Okay, so minus r squared. So we'll put here r is constant. And the r itself, the little r, if this is the center, and say a layer of blood, Okay, so think about like, red blood cells. Say you have a whole bunch of red blood cells like in a line like this moving. This is the very center. And then there'll be, say, a layer beside them. This is an approximation, okay? And then another layer. So the radius R is this first layer of blood from the center. Okay, and red blood cells are, a specific size roughly. So that radius is going to be constant, even though the vessel is contracting. Okay, so that's going to be our little r. And the capital R, the thing that's overall changing, is right here. Okay, so that's our capital R. Okay, so this is our expression, and this is what we need to differentiate. Okay, so I'm going to go dv dt, because I'm differentiating with respect to time, is equal to 375, and I'll leave that there for now. So the first term, by power rule, I'm going to bring down the 2. I have my capital R. You can write r of t if you want to, but I'm not going to because I know it's a variable. And then by chain rule, I have d capital R dt. And because the little r is a constant, this second term, well, that's just equal to 0. Okay, so 375 times 2, so that's going to be 750. And what do I know? Do I know R, capital R? Yes. Suppose blood vessel has a radius of this. So before I do that, let me put a little remark here. So we are told that R is going to be equal to 0.08 millimeters. And I'm also told that dr dt is equal to 0.01 millimeters per minute. But I have to be a little careful with how this is phrased, because it says in English, the cold weather is causing the vessel to contract at a rate of blah. Contract means it's getting smaller. So even though the question didn't put a negative here, it said it in English. So really we have a negative out front. Okay, so be really careful about that. So now that I know those two quantities, let me go back here to my derivative. My capital R is going to be 0.08. And then this is times negative 0.01. Okay, when we multiply those together, we're going to get a negative value, 0.6. Now, in terms of units, this is a velocity. A velocity is what? We usually think of like meters per second. In our case, we're being told we're doing things in millimeters and minutes. So we have millimeters per minute, okay, for the top quantity. But then I'm looking at the rate of change of time. Okay, so this is millimeters per minute per minute. Remember, the rate of change of velocity is acceleration. So you can think about it as also millimeters per minute squared, if you want to write it that way. You don't have to. It's up to you. And since it's negative, it means that the velocity is going to be decreasing at that particular rate. So the velocity of the blood is therefore decreasing at a rate of dv dt is equal to negative 0.6 millimeters per minute per minute. Okay, so hopefully you found that helpful, and I'll be posting some extra problems with this as well, so you can see a few more examples.